March 1945. American intelligence officers pry open the engine cowling of a captured Messerschmitt Me-262 at Frankfurt Airfield. When engineers disassemble the Junkers Jumo 004 turbine, they discover something that defies belief. The turbine blades, components spinning at thousands of revolutions per minute in temperatures exceeding 800 degrees Celsius, are made from chromadur, a crude steel alloy containing 70% iron, 18% manganese, and 12% chromium. No nickel, no cobalt, no molybdenum. The world's first operational jet fighter uses Bronze Age metallurgy in its most critical component. The consequence is devastating. The average Jumo 004 engine lasts just 25 hours before complete failure. Pilots must conduct full engine overhauls every 10 hours of flight time. By comparison, Allied piston engines run for 100 hours between overhauls. This is how material science, not enemy pilots, crippled the most advanced aircraft of World War II. But this wasn't just any jet fighter. The Me-262 represented the absolute pinnacle of wartime aviation technology. Flight tests after capture confirmed a top speed of 540 miles per hour, over 100 miles per hour faster than any Allied fighter. The jet carried 4 devastating 30mm Mk-108 cannon. Elite Me-262 units achieved kill ratios exceeding 4-to-1 against Allied bombers. On March 18, 1945, Me-262S destroyed 12 flying fortresses while losing only 3 jets. German propaganda called it the Wunderwaffe, the wonder weapon. Yet despite producing 1,443 airframes, only 300 Me-262s ever reached combat deployment. At any given moment, fewer than 100 were operationally ready. The majority sat grounded, waiting for engine replacements. How could the most dominant fighter per engagement have virtually no strategic impact? The answer lies in a metal Germany couldn't acquire: nickel. Getting their hands on an intact Me-262 required moving fast. The US Army Air Forces launched Operation Lusty, Luftwaffe secret technology. Colonel Harold Watson led the team nicknamed Watson's Whizzers. Their mission: capture German jets before Soviet forces seized them. The breakthrough came March 31st, 1945. German test pilot Hans Fey defected, flying a brand new Me-262A1 directly to Frankfurt Rhein-Main airfield. The unpainted jet, serial number 500,491, provided pristine engines for examination. Allied engineers transported the engines to specialized facilities. The Royal Aircraft Establishment at Farnborough handled flight testing. NACA conducted metallurgical analysis in the United States. When metallurgists examined the turbine section, they focused on the area experiencing maximum thermal stress. The turbine blades were hollow and air-cooled, sophisticated design. The cooling channels were precisely manufactured, but spectrographic analysis revealed the shock: complete absence of essential high-temperature alloying elements. The blades were stamped from sheet metal, then folded and welded. The iron-based chromadur simply couldn't maintain structural integrity at operational temperatures. Where Allied turbines used nickel-based superalloys, the Germans used modified steel. Engineers identified the failure mechanism: thermal creep. Under intense heat and centrifugal forces, the inferior alloy blades slowly stretched and deformed. This created catastrophic vibration imbalances. Eventually, elongated blades rubbed against the engine casing, generating heat and friction until complete disintegration. The testing records told everything. The initial 004A prototype engines, built without material restrictions, had completed 150 hours of operation. The production 004B model substituted scarce alloys. Engine life collapsed to 10 to 25 hours. The reason wasn't incompetence. It was desperation from Germany's strategic metal blockade. Dr. Anselm Franz designed the UMO-004 at Junkers Motorenwerke. He selected an 8-stage axial flow compressor, the world's first production axial flow turbojet. The narrow diameter offered reduced drag. The aerodynamic efficiency was superior, but axial flow created exponentially greater stress on turbine components. The prototype 004A used nickel-cobalt-molybdenum superalloys. These materials maintained strength at temperatures exceeding 800 degrees Celsius. They resisted creep and endured punishing rotational forces. By 1943, Germany couldn't secure these metals. The Allied blockade was absolute. Nickel came from Canada, cobalt from the Belgian Congo, molybdenum from Allied-controlled deposits. The Reich Air Ministry ordered France to redesign using only non-strategic materials. Krupp developed chromadur as an emergency substitute. High iron content made it cheap and abundant, but iron-based alloys have catastrophic creep resistance at jet turbine temperatures. Germany made a calculated decision. Optimize for production volume, not longevity. They manufactured 8,000 JUMO-004 engines, not to equip 8,000 aircraft, but as consumable replacements. Each engine was disposable, like ammunition. Compare this to Allied development. Britain's Rolls-Royce Derwent used a centrifugal flow compressor. Centrifugal designs are heavier but operate at lower temperatures with less stress. Rolls-Royce had unrestricted access to nickel-based superalloys and precision forging. The Derwent achieved lifespans exceeding 150 hours, 6 times longer than the JUMO-004. In combat, the material weakness created tactical vulnerabilities beyond maintenance. The JUMO-004 was brutally unforgiving. Pilots received explicit warnings. Never advance throttles rapidly. Sudden power demands caused flameouts or thermal shock. This throttle lag, sometimes several seconds, crippled maneuverability during dogfighting. The poor acceleration at low throttle made the Me-262 helpless during takeoff and landing. Pilots were forced into predictable flight patterns that Allied fighters learned to exploit. Once Allied intelligence understood the weakness, tactics transformed. Commando Nowotny formed in August 1944 as the first jet fighter unit, commanded by Major Walter Nowotny. During September to November 1944, they claimed 19 Allied aircraft destroyed. They lost 6 Me-262s, but most German losses came from mechanical failures and ground attacks, not aerial combat. Jägergeschwader 7 demonstrated the jet's lethality on March 18, 1945, destroying 12 bombers for 3 jet losses. In perfect conditions, the Me-262 was untouchable, but even elite units struggled with low readiness rates. Formations planned with 30 aircraft launched with only 8 or 10 airworthy. American and British pilots developed airfield capping tactics. P-51 Mustangs loitered above known jet bases like Lechfeld and Munchenriem. Then they waited. When Me-262s began landing, Mustangs dove on them. During final approach, jet pilots couldn't rapidly advance throttles without risking flameout. The throttle lag meant seconds of complete vulnerability. Before these tactics spread, Me-262 pilots relied on overwhelming speed. They blasted through formations and zoomed away before anyone could react. After Allied pilots exploited the landing vulnerability, German attrition skyrocketed. The Luftwaffe installed dense anti-aircraft batteries along approach corridors, flak alleys. The world's most advanced fighter required World War I defenses to survive returning home. The engine drain also limited training flights. New pilots entered combat with sometimes less than 10 flight hours in type. This lack of proficiency compounded losses. Germany manufactured 1,443 airframes but never achieved operational mass. Keeping one Me-262 operational required more resources than maintaining an entire squadron of piston fighters. The examination of captured Jumo 004 engines revealed Bronze Age metallurgy in Space Age machinery. Understanding why Germany accepted this compromise exposed their complete strategic desperation. The Jumo 004's axial flow architecture established the design template for all future jet propulsion. Post-war American and Soviet designers universally adopted the German axial flow model. Dr. Anselm Franz immigrated to the United States under Operation Paperclip. He developed reliable turboshaft engines for Lycoming, powering American helicopters throughout the Cold War. But the Me-262's failure proved an invaluable lesson. Revolutionary design requires equally revolutionary materials. Germany's inability to secure strategic metals, nickel, cobalt, molybdenum, doomed their most advanced weapon before the first combat sortie. The Me-262 program functioned as an industrial sinkhole, consuming irreplaceable resources without proportional returns. Revolutionary airframes waited months for replacement engines that manufacturing couldn't supply fast enough. The most sophisticated aircraft of World War II was defeated not by Allied pilots, but by the periodic table itself. Advanced weapons are only as effective as the supply chains that sustain them. Germany learned this lesson at tremendous cost.